Roadmap to Clean Energy Using Laser Beam Ignition of Boron-Hydrogen Fusion. Number 3. Cylinder Targets Properties for a Laser Boron Fusion Reactor. Laser ignition of fusion in a cylindrical full targets is in indifference to the most studied spherical ignition with adiabatic plasma compression and thermal ignition. For cylindrical ignition, the studies of plane laser waves at normal incidence on a plane plasma target are of interest in one dimension. The computations are including the forces from the gas dynamic plasma pressure, but on top, there is a further pressure from the electrodynamic laser field which can dominate over the thermal forces if the laser has a sufficiently high intensity. Figure 4 is the result where deuterium plasma laser with critical density at x equals 0 density not far from the solid state is irradiated by a neodymium glass laser with 10 to the 18 power watt per centimeter square intensity from the right hand side. The full drawn line is the density of the laser energy given by the electric E and magnetic B field of the laser. The intensity at the vacuum at the right side end is increased in the plasma due to the optical constant, like in glass, resulting in an increase to a maximum and into a deeper decay due to absorption, similar to metallic absorption of light. The negative gradient of this curve produces a nonlinear force in the plasma, which is much larger than the gas dynamic force for an initial plasma temperature of about 1 million degrees, and despite further heating by the laser, that all is carefully included in the computation. 1.5 picoseconds after the laser interaction, the non-thermal laser force accelerated the plasma to the velocity shown in the dashes line. There is a plasma block moving with a velocity above 10 to the 9 power centimeter per second against the laser light in the outer part, and another block moving into the deeper part of the deuterium. The acceleration for those blocks has the astronomical value above 10 to the 20th power centimeter per second square. The result of figure 4 was from computations in 1978. The necessary picosecond laser pulse of the power of up to petawatt were available only in 1990 6. The measurement of the plasma blocks was then possible, figure 5, but by survey from the dipolar blue shift of special lines in the reacted light arriving at the theoretical predicted value of the ultra-high acceleration above 10 to the 20 power centimeter per second square. This was about 100,000 times higher than any acceleration measured in a laboratory. The experiment was not easy to be reproduced by well repeated soon by Ford's et.al. The non-linear force-driven ultra-high accelerated plasma blocks had a further extreme property. The space charge neutral plasma blocks had ion current densities more than million times higher than any classical ion accelerator could produce. It was then possible that the picosecond petawatt laser pulse produced the ultra-high density accelerated ion pulse of few to several hundred mega-electron-volt ions. This was measured in agreement with complicated computations. Interestingly, the acceleration could be calculated in a transparent and understandable way by the genuine multifold hydrodynamic models needed for hadron cancer therapy. This completed hydrodynamics demonstrated for the first time directly how inhomogeneous plasma has very high internally electric fields and their dynamic changes. For ignition of laser fusion, the plasma blocks were needed for the first general use of the initiation of fusion reactions by picosecond laser pulse irradiating uncompressed solid-state fuel, tube, and bobine. Evaluated the laser properties for igniting uncompressed solid density fusion fuel. The result was that the initiation of a fusion reaction needed an impact of an energy flux of 4 times 10 to the 8th power joule per centimeter square during 1 picosecond as a threshold for generating a fusion flame in DT. For the computation, the above described non-linear force-driven plasma block generation could then be used, and the later known plasma phenomenon had to be included for reproducing the ignition of DT. It was then a surprise when using the fusion cross sections of HB11 were used in the calculations. The threshold for B11 were nearly the same. As for DT fusion, ignition of HB11 was then happening at 5 orders of magnitude higher thresholds than the classical HB11 fusion at thermal equilibrium. These computations use the single field hydrodynamics as true using the genuine two-field code, arrived at the same ignition but by many more details of shock generation and thermal plasma effects beyond the analytical result of the Rankine-Hugoniot theory. The reaction rate in solid state HB11 fuel, depending on the depth x of the fuel at different time, is shown in a case of Fig 6. The reaction front moves with the velocity is a range of 1000 km per second, which value is similar as known from explosive nuclear reactions. It is remarkable generation of the shock density profile as it is building up very much later than the picosecond plasma block ignition of the reaction. This delay is 500 picoseconds and more. The one-dimensional conditions were nearly sufficiently well given in the experiment of Savelli, or later for clearly demonstrating that the generated plasma blocks were generated in the skin depths of the irradiated plasma, as seen from the unchanged numbers of the ion in the first blocks at varying laser intensities at the same focusing in order to take care of the restricted laser beam diameter and to produce a cylindrical geometry of the reaction as shown in Figure 3. The trapping of the reaction at a constant radius is necessary. This can be done by the ultra-high magnetic field by the laser-produced plasma with the plates as shown in Figure 3. Figure 7 shows the result of trapping of the plasma to the initial radius of 1 millimeter by a magnetic field of 5 kilotesla. Is event the number of the generated alpha particles is shown at different time. The radial trapping at different times is confined and increasing on time, indicating the successful ignition. Parallel to these development with computations of binary fusion reactions for HB11 similar to the computations using DT, the measurement of highly increased fusion gains with boron, was not only clarified by comparison with gains from DT for confirming the avalanche multiplication of generating each 3 alpha particles per reaction, evaluating the experiment by elastic collisions within the extremely non-equilibrium plasma confined the avalanche process in all details. Figure 8. Summarizing all the mentioned process permitted the computation that the single beam direct drive HB11 fusion in the cylindrical trapped fusion plasma with end-on direct drive plasma block ignition will produce a very high energy gain. The final result for a power reactor of Figure 2 will then result in the reaction of 40 mg boron-11 with the proton of hydrogen generating more than 1 gigajoule energy. The single laser beam for the ignition has to be a picosecond laser pulse of 30 kilojoule energy of 30 picowatt power. Which kind of pulses are rather close to the state of the art if needed to 1 shot per second for energy generation of the value of more than 100 million per year. Thank you.